DNA digital data storage, the future is in our genes. Hello, and welcome back to AI Mind Blowing. If you're passionate about the intersection of technology and the human experience, make sure to hit that subscribe button below. Today, we're delving deep into a mind-blowing technology that could redefine the way we store and manage data, DNA digital data storage. Yes, you heard that right. So, let's dive right in. Humans are producing millions of gigabytes of data every day as digitalization spreads quickly. By 2025, the total amount of data generated worldwide will be around 180 zettabytes. 1 ZB equals 1,012 gigabytes. It is quite difficult to find cost-effective storage options for such a vast volume of data. Professor of Biological Engineering at Tianjin University Ng Yuan used deoxyribonucleic acid, DNA, to solve the problem and created yeast artificial chromosomes as a viable solution. DNA has evolved to be extraordinarily stable and can store enormous amounts of information at very high density. Up to 250 million base pairs of DNA make up the human chromosome with the biggest size. The total amount of data in the world could theoretically fit in a coffee cup if it could be stored on every base pair. A single-cell creature called yeast normally has 16 chromosomes. Yuan's team has created and synthesized an additional yeast chromosome in a live cell using a synthetic biological approach. Scarified low-density parity check, LDPC, codes, a technique for conveying a message across a noisy transmission channel, and pseudo-random sequences were used in their ingenious error-correcting encoding system. The computer files were then converted into code words and finally into synthetic DNA fragments. These DNA fragments were then put together to create a synthetic chromosome. This method results in an artificial chromosome with a capacity of 254 kilobases, 1 kb equals 1,000 bases, of DNA. 2 images and a movie were successfully saved there by the team, and the encoded data takes up more than 95% of the sequence one. According to Yuan, our work exceeded the current DNA data storage limit of only a few thousand bases per genome. What is DNA digital data storage? DNA, or deoxyribonucleic acid, is the biological blueprint for life as we know it. But scientists are now leveraging its unique properties to store digital data. Think of it as a biological flash drive. In a world flooded with data, figuring out where and how to store it efficiently and inexpensively becomes a larger problem every day. One of the most exotic solutions might turn out to be one of the best, archiving information in DNA molecules. The prevailing long-term cold storage method, which dates from the 1950s, writes data to pizza-sized reels of magnetic tape. By comparison, DNA storage is potentially less expensive, more energy efficient, and longer lasting. Studies show that DNA properly encapsulated with a salt remains stable for decades at room temperature and should last much longer in the controlled environs of a data center. DNA doesn't require maintenance, and files stored in DNA are easily copied for negligible cost. The concept isn't as far-fetched as it sounds. DNA has been storing complex biological data for billions of years. So why not our spreadsheets and selfies, right? Why DNA? Current data storage technologies like hard drives and SSDs are reaching their limits in terms of speed and capacity. Plus, they have a limited lifespan and are prone to failure. Most people associate DNA with life, not computers, when they think about DNA. However, DNA is a 4-letter code that carries information about a creature. The 4 different bases, or nucleotides, that make up DNA molecules are adenine, A, thymine, T, guanine, G, and cytosine, C. They serve as the foundation for all DNA coding and serve as the building blocks for all life on Earth. Although the approach has been successfully tested, it currently takes a considerable time to read and write DNA-encoded information. It takes roughly 1 second to add 1 nucleotide to DNA. At this rate, writing an archive file could take decades, but research is producing quicker techniques, such as massively parallel processes that write to many molecules simultaneously. DNA is incredibly dense and stable, meaning it can store vast amounts of data for thousands of years without degradation. Imagine storing the entire Library of Congress in a test tube. How does it work? Scientists convert digital data into DNA sequences. Your ones and zeros become a series of A, T, C, and G, the 4 nucleotide bases of DNA. Then, they synthesize actual DNA strands based on these sequences. The ADS Codex explains precisely how to convert zeros and ones into sequences of the letters A, C, G, and T. The decoding back into binary is also handled by the Codex. ADS Codex can support all the different ways that DNA can be made. Unfortunately, writing to molecular storage with DNA synthesis has far higher error rates as compared to conventional digital systems. These problems are more difficult to fix because they come from a different source than they do in the digital age. Binary mistakes happen when a 0 turns into a 1 or vice versa on a digital hard drive. The insertion and deletion mistakes in DNA cause issues. If you're writing ACGT, for instance, but occasionally you try to write A, and nothing appears, so the sequence of letters shifts to the left, or it types AAA. With such kind of issue, standard error correction codes are ineffective, hence ADS Codex includes error detection codes that verify the data. The software checks to confirm that the codes match before converting the data back to binary. If they don't, the verification process eliminates or adds bases, letters, until it is successful. DNA can store an incredible quantity of data in a very tiny volume. Consider this, by 2025, humans will produce 33 zettabytes of data, or 3.3 followed by 22 zeros. All of that data can fit comfortably inside of a ping-pong ball thanks to DNA storage. The 74 million bytes of data in the Library of Congress could be packed 6,000 times more information into a DNA repository the size of a poppy seed. The entire Facebook dataset could be stored if the seed were split in half. Smart Scale-Up. We have completed version 1.0 of ADS Codex, and late this year we plan to use it to evaluate the storage and retrieval systems developed by the other MIST teams. The work fits well with Los Alamos' history of pioneering new developments in computing as part of our national security mission. Since the 1940s, as an outcome of those computing advancements, we have amassed some of the oldest and largest stores of digital-only data. It still has tremendous value. Because we keep data forever, we've been at the tip of the spear for a long time when it comes to finding a cold storage solution, but we're not alone. All the world's data, all your digital photos and tweets, all the records of the global financial sector, all those satellite images of cropland, troop movements, and glacial melting, all the simulations underlying so much of modern science, and so much more, have to go somewhere. The cloud isn't a cloud at all. It is digital data centers in huge warehouses consuming vast amounts of electricity to store and keep cool trillions of millions of bytes. Costing billions of dollars to build, power, and run, these data centers may struggle to remain viable as the need for data storage continues to grow exponentially. DNA shows great promise for sating the world's voracious appetite for data storage. The technology requires new tools and new ways of applying familiar ones. But don't be surprised if one day the world's most valuable archives find a new home in a poppy seed-sized collection of molecules. To retrieve the data, the DNA is sequenced and converted back into digital format. Voila! You have your data back, exactly as it was. Applications. The applications are limitless. From archiving historical documents to storing medical records, and even safeguarding the digital treasures of humanity for future generations. Major tech companies and research institutions are already investing in this groundbreaking technology. So, it's not just a concept, it's the future knocking at our doors. Challenges and ethical considerations. Of course, it's not all roses. There are challenges like cost, data retrieval speed, and ethical considerations, such as data privacy and potential misuse. That's it for today, folks. If you found this episode enlightening, give it a thumbs up and share it with your friends. Comment below with what you think about DNA digital data storage. Will it replace our current storage devices? Let's discuss. You've been watching AI Mind Blowing. Don't forget to subscribe for more mind-bending tech content. Until next time, keep exploring the future.